SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 3 of Aerospace Structural Analysis. Today we will start with a brief recap of the basic equations of theory of elasticity, which we will be using widely during the rest of the course. So, we will just get reacquainted with certain basic equations of elasticity, get acquainted with the terminologies that we will be using throughout the course. So, So, let us start with the equations of equilibrium. So, let us consider a generic 3D body and let us draw the 6 stress component, the 6 stress components that occur in a generic 3D elastic body. So, we have this 3D elastic body. I have drawn the coordinate axis as well. Let me just draw the stresses and strains. So, the stresses, the normal stresses and the shear stresses. So, I have sigma x here, I have sigma y here, the normal stresses, and I have sigma z. Apart from these 3 normal stresses, I will have the shear stresses, which is tau x y, tau x z, So, these are the 6 stress components that we have for a generic 3D elastic body. So, the normal stresses are sigma x, sigma y and sigma z, and the shear stresses are tau x y, tau y z and tau x z. This again, as we know, the complementary shear stresses are there, which is equal to each other. Now, from the equilibrium of this 3D generic body, from the force equilibrium of this 3D body, we can write down 3 equations of equilibrium. The 3 equations of equilibriums that is obtained by the force balance can be written like this. Where x is the body force, per unit volume that is acting on the body. So, this body force could be the weight of the body, the gravitational force, it could be the inertial force, the centrifugal force that acts on a body. So, this is the body force per unit volume. Then similarly, I have two more equation, which is similarly, y is the body force per unit volume in y direction. This is in x direction and this is in y direction. The next equation that we have can be written as, all of us are well acquainted with this equation, but this is just for the completeness and to get reacquainted with the equations that we will be dealing a lot with in the coming lectures. Okay. So, these are the three equations of equilibrium. So, a body under any form of stresses, any set of normal and shear stresses should follow this should satisfy this three equilibrium equation in order for the body to be in equilibrium. So, apart from these three equilibrium equation, the stresses should also satisfy the boundary conditions that are there for any generic 3D body. So, let us get into the next set of boundary conditions that we have for any 3D body. So, let me just erase this off. And let me draw the Now, let us consider this tetrahedron on the boundary of the 3D body, any arbitrary boundary of the 3D body. Let x hat, y hat and z hat be the surface forces on the boundary. Surface forces per unit area. So, x hat, y hat, z hat are the surface forces acting on this boundary of area A per unit area. Okay. Now, the boundary condition that the stresses need to satisfy is given as x hat should be equal to sigma x into L where L is cos n x where n is the normal on the surface, on the boundary surface, x is the x axis. So, L is cosine of the angle between the normal n to the surface and the x axis. Similarly, m is cosine of the angle between the normal to the surface and the y axis, and so is n cos n z. Okay. So, similar to the equation for x direction, we have two more equations, boundary conditions for the y and z direction. So, it will be written as tau x y into L plus sigma y into m plus tau y z into n. So, these are the three boundary conditions that the stresses need to satisfy along with the three equilibrium equation that we have just derived. So, now this is the first set of equation that one needs to know. Perhaps all of you all have gone through this equation during your courses on solid mechanics and theory of elasticity. Now, as we know that there are six unknown stresses and we have only studied three equilibrium equation. Therefore, this becomes an indeterminate, statically indeterminate problem, and to solve for the to uniquely solve for the 6 stress component, we will need another 3 set of equation that will give uniqueness to the solution for the stresses sigma x, sigma y, sigma z, and tau x y, tau y z, and tau x z. So, as many of you all might be knowing that the additional 3 equations are the compatibility conditions that comes in terms of certain constraints or condition on the associated strains. So, the compatibility conditions are actually very lengthy looking equations that are given in any conventional textbooks on theory of elasticity. So, what we will do, we will write down the simpler equations relating the strains with the displacement, and which could be further processed or further worked on to get the equations conditions for compatibility. So, let me write down the strain displacement relations which will eventually give you the compatibility conditions. Instead of remembering the long compatibility conditions, it is often more easier to remember the strain displacement relation and later derive the compatibility conditions from the strain displacement relation. So, the strain displacement relations are given as epsilon x is equal to del u by del x, where u is the displacement in the x direction and epsilon x is the normal strain in x direction. Similarly, we have epsilon y equals to del v by del y, where v is the displacement in y direction. And then we have epsilon z So, these are the 3 normal strains, and then we have the shear strains, which is written as gamma x y, which is del u by del y plus del V by del x. Similarly, so these are the shear strains. So, these are the normal strains and these are the shear strains. So, if we further work on this equations that we have, we can get a set of 3 relations between the normal strains and the shear strains, which are called the compatibility conditions, which are kind of constraints which are required to get an unique solution for the stresses and therefore the strains. The other importance of the strain displacement relation is that we can obtain the displacement functions, that is u, v and w, once we know the strains in a body using these relations. So, apart from the strain displacement relation, there are 6 more equations which denotes the stress strain relation that also we need to keep in mind and we will be using in the rest of the course. So, let me quickly write down the stress strain relation that is required for all the derivations that we will be doing in the later part of the course. So, the stress strain relation is obtained in terms of the Young's modulus and the shear modulus. So, the epsilon x can actually be written as 1 by E, where E is the Young's modulus. For an isotropic material, I have sigma x minus nu, nu being the Poisson's ratio, into sigma y plus sigma z, sigma z. So, this is also sometimes called the generalized Hooke's law. So, let me write down, this is the Young's modulus and this is the Poisson's ratio. Okay. So, similarly, the other strains can also be written as 1 by E So, apart from this 3 relation for the normal strain, so this is for the normal strain. We will have 3 more relations relating the shear strains with the shear stress. So, the relations are gamma x y, which is one of the shear strain, is 1 by g into tau x y. Similarly, gamma y z is 1 by g into tau y z, and gamma x z is 1 by g into tau x z, where g is the shear modulus. So, in summary, we can say that the 3 equilibrium equations that we have derived, the 3 boundary conditions, the 3 compatibility conditions and the 6 stress strain relations are the ones that we need to keep handy whenever we are going to solve a problem pertaining to aerospace structures. So, as we go through the course, you will see that we will be using these equations very often, very commonly, to derive more advanced theory for thin walled aerospace structure. So, this is eventually going to lead us to compatibility conditions. So, I have given a very brief recap of the basic equations and theorems of theory of elasticity, just to start with the aerospace structural analysis, with the assumption that most of the audience that we have for this course have already a working knowledge of theory of elasticity. If you need to know further about the theory of elasticity and how these equations are derived, you probably need to go through some textbook. One of the good textbook is the textbook by Timoshenko, The Theory of Elasticity. So, that book I mostly follow that book, and it is a good book to follow to get a recap of the theory of elasticity. So, next we will be solving the problem of torsion of a shaft with circular cross section. So, most of you all have solved the problem of or studied the problem of torsion of a shaft with circular cross section in the previous courses that you have done, in any solid mechanics course or structures course that you have done. But we will be solving the basic problem of torsion of circular shaft that you have already studied in the light of elasticity, so that it helps us, it gives us a very simple introduction to the further slightly more complex problem of aerospace structures. So, let us start with torsion of shaft with Okay, so let us get back to the problem. So we have a cylindrical shaft. The cross section XX, as I have drawn, is circular. So it is an uniform circular cross section shaft. The coordinate axis x, y, z are shown. A torsional moment MT is acted on the shaft. An equal and opposite MT is acted on the shaft, so that it is in equilibrium. So, as many of you all might be knowing that there are certain features of torsion of circular shaft. So, let me just quickly write down the So, the first point that you all might be knowing about the torsion of circular shaft is that the circular cross section of the shaft, the first feature is that the circular cross section of the shaft remains circular after the twist. Okay. So, even after we apply a torsional load to the shaft, the cross section of the shaft is going to remain circular. There is not going to be any change in the cross sectional shape of the shaft, if it is a circular shaft. The second point that you might be knowing, that the problem of torsion of a circular shaft is a problem of shear, pure shear. So, the only stress that will act on the shaft will be a shear stress. There will be absolutely no normal stress in the shaft. So, it is under pure shear. The third point is that there will be no out of plane deformation of the cross section, or there will be no out of plane warping of the cross section. So, there will be no So, there will be no out of plane warping or deformation. So, or in other words, we can say that the plane circular cross section will remain plane after the twist. The fourth point is that d phi by dz, which can be written as theta, is constant, where phi is the angle of twist. Okay. So, the rate of change of angle of twist with the lengthwise axis, that is the z axis, is constant. Okay. So, this is another important feature of the torsion of circular shaft. The fifth point is that the shear stress that we have talked about is going to be directly proportional, the shear to the radial length from the center of the shaft. So, the shear stress at any point of the stress of the shaft is directly proportional to the radial distance of the point from the center of the shaft. So, this So, all these basic features of torsion of the circular shaft is already known to you. In the next lecture, we will use the theory of elasticity and try to revalidate these points as we derive the equations for the torsion of a circular shaft. Thank you.